Okay, now I want to compare between electron microscope and optical microscope. So what is so good? What is so good about electron microscope compared to the usual optical microscope in your lab, yeah, in your school lab? Electron microscope can only be found in the university, yeah, but in your school lab you only have optical microscope. Okay, so electron microscope is very good, yeah. So first thing is electron microscope, you don't use the light beam. Electron microscope use the electron beam, and the beam they use is electron. But optical microscope they use light ray, yeah. The difference between electron and light is electron is a charged particle, but light is an uncharged particle, and that makes all the difference. Understand? Electron is a charged particle, light is an uncharged particle. So in short, what I can say is electron can be accelerated, but light cannot be accelerated. You just take what the wavelength it is. Okay. So again, why electron microscope is so good? Because the electron can be accelerated. But why optical microscope is not as good? Because the light cannot be accelerated. Yeah, light is like a photon, no charge at all, uncharged, so cannot be accelerated. So what wavelength you have for light, you just use the wavelength. But electron, you can manipulate the wavelength. Remember how do you manipulate the wavelength? That's why about the electron diffraction just now, I'm talking about the accelerating chamber. Accelerate the electron. When you accelerate the electron, because the wavelength, according to de Broglie, the wavelength is influenced by the velocity. Why you need to accelerate the electron? Because the wavelength of the electron is influenced by the velocity of electron. And if you have a very high velocity, you have a very small wavelength. When you have a very small wavelength, you have a less diffraction. When you have a small wavelength, what happens when you have a small wavelength? When you have a small wavelength, you have a less diffraction and you get a sharper image. That's the conclusion. You understand? That's all about it. Okay. So, but light is uncharged. The light ray cannot be accelerating. You cannot put the light ray into accelerating chamber attracted by the positive plate. How do you attract the photon light? Photon is uncharged. How do you attract the photon by the positive plate? Yeah, cannot, isn't it? Only the electron. Electron is negative charge. It can be attracted by the positive plate, so it can be accelerated. Go back to this electron microscope. So the difference between electron and the light is electron is a charged particle which can be accelerated, but light is uncharged particle which cannot be accelerated. And light normally has very long wavelength. But the electron wavelength can become very short. Can achieve very short wavelength. What I can say is not electron not naturally very short wavelength. What I can say, it can achieve. The word I say, can achieve very short wavelength. The electron can achieve very short wavelength of electron. How to achieve small wavelength of electron? By accelerating chamber. Remember the accelerating chamber, which is using this formula, EV equal to half mv square. That means you apply a very high voltage, potential difference between the cathode and anode, high voltage. You will get a very high velocity electron. At very high velocity electron, very high momentum, very high velocity electron, the the wavelength can be reduced into a very, very short wavelength. So the wavelength of electron can achieve very, very short wavelength. Very, very short wavelength. We can say it can achieve until the wavelength of electron can become 1/100 of wavelength of light. That means wavelength of electron is 100 times shorter. 100 times shorter by the wavelength of light. Compared to the optical microscope, wavelength of electron is 100 times shorter. 100 times shorter. That means if optical microscope is let's say 100 cm. Let's say the wavelength of light is 100 cm. Maybe I just write that wavelength of light, let's say, is 100 cm. Then the wavelength of the electron is just 1 cm. Very, very short. You understand? But this is just example lah. This is just example. Okay. So and then the resolving power or resolution, or we can say the sharpness of image. Resolving power is the how you resolve. That means resolve. You understand how to resolve? Resolve vector. You know what is resolve vector? You know what is resolve vector? You know what is resolving power? You know what is resolve vector? That means originally I have one vector I resolve into two components, isn't it? Let's say I have force, this one. I can resolve into two components, right? You can have fx and fy, resolve into two components. So when we say about resolving power, what does it mean by resolving power? Resolving power. What does it mean by resolving power? Resolving power is like the power to resolve, the power to differentiate details. What I can say is the power to differentiate details. Okay, you see, maybe one very simple example. Do you have high resolving power? Let's say you have these two lines. You can see from here. Okay. Now I have a very good example here, because this laptop has a zooming ability, so I really like it very much. Maybe I just show you. You see this line, these two line. Okay, this line. Look at this line again. Let me rub it off. I don't like this line and this line. Put it okay. Now here you can see. You resolve into two. Easily you can resolve into two, isn't it? You can easily resolve into two. But what if now you're looking very near, you can see resolve into two. Maybe I should write it sorry, again. Now I can see resolve into two easily. Resolve into two. And I can see resolve into two easily, isn't it? Now your resolving power, resolving power, resolve into two. I can see details. You have two lines here. Now if I zoom out very, very far away, what can you see now? Do you have high resolving power enough? I should put it over here. I should put it over here. Okay, now you still can see it is two line, isn't it? You can see in two line. What if very, very far away? Oh, this is the maximum. Can you still see it as two line? Yeah? Maybe not small enough. Maybe I should make it even. Maybe I just use two line here. Okay. Now maybe this one, maybe this line. Now you see as two different lines. What if you zoom in out? Zoom in out, zoom in out. Now what can you see? What can you see? Can you see it's two different lines? Can you still see it as two different lines? Electron microscope can still see it as two lines. You understand? Can still, because it has high resolving power. It still can separate it into two. That's what I mean by resolving power. Now your eyes only can see as one line, isn't it? You can only see it from one line because it's very small. It's very small. Your eyes can, maybe the optical microscope can only see in one line, but electron microscope can still see in two lines. Can still see in two lines. This is what I mean the resolving power. Okay, do you get the idea? Resolving power is the power to differentiate details. That means if you have a very small, let's say virus is so small, you can't see it, it's so small. Electron microscope has a high resolving power enough to see all the tentacles, all the structure is a round shape instead of just a dot. You see a round shape, or it's shaped like this. Yeah, this is electron microscope can do. It can see a very 100 times smaller nanometer. Plant cell, animal cells. Okay. Now that's a high resolving power. Understand? Just take this example. Where is my too small, and I don't know where is it. This one. Yeah, I like this example. Now you still can see it because it's big. But what if it become very small, like a virus? Like a virus, a bacteria. Can you see the details? The details. Can you still see it as two lines instead of one line? I see it as one line already. Now I only see it as one line. Only one line. I cannot differentiate anymore. My eyes, even though I have 4 eyes, my resolving power is not high enough. But if you use electron microscope, you still can see it as two lines. Okay. Okay, because the okay, that's it. Yeah. Okay. Now, what I can say is why. The question is, electron microscope can see a very small object. Why the thing is, why electron microscope can see such a small object? It's all because of the wavelength, the de Broglie wavelength, because the electron can be accelerated to a very high velocity, where at very high velocity it can achieve a very small wavelength. Yeah, you actually why it can achieve a very small wavelength, you can actually just use the formula wavelength is equal to h over square root 2m 2mev. Why the wavelength of the electron can become so small? Because electron can be its charged particle can be accelerated. It can be accelerated by a potential difference by a very high. So you can manipulate the wavelength of electron by changing by applying high potential difference, or high voltage, or high potential difference. You can manipulate, you can manipulate the wavelength of electron. You can manipulate the wavelength of electron by using high voltage. Using high voltage. If the higher the voltage you use, the smaller the wavelength of electron can be. But the light cannot be manipulated. The light wavelength, since the light cannot be accelerated, the wavelength of light cannot be manipulated. It cannot change. You cannot change. That's why the optical microscope, no matter how good it is, it always limited, because you cannot manipulate the wavelength. It cannot. The wavelength of the light cannot be manipulated. Okay. So you can make the wavelength of electron you can make the wavelength of electron very, very small by applying very, very high voltage. Okay, because very high voltage, it has very high velocity. At very high velocity, according to de Broglie wavelength, very high velocity, at very high velocity, the wavelength of electron become very, very small. So now, the smaller the wavelength, the higher the resolving power. Yeah, the resolving power is inversely proportional to the wavelength. The smaller the wavelength, that means the less diffraction. Less diffraction means sharper image. Get a sharp image. You see, if you look at the image, the sharper image. Sharper image means high resolving power. High resolving power. So the resolving or resolution of the resolving power of the electron microscope is 100 times the resolving power for the light microscope. So for the, you can say the wavelength of electron is very, very short. The wavelength of the light is very, very long. Okay. So for the resolving power, what I can say is the resolving power of the electron is very high, but the resolving power for the light microscope, is very low. Okay, because the electron has very small wavelength. Very small wavelength means very high resolving power. But the light has very long wavelength. Long wavelength means more diffraction. More diffraction means blur image. Blur image means low resolution. Low resolution means low resolving power. Okay, so resolving power is inversely proportional to the wavelength. So what I can say is wavelength of electron is 100 times shorter than the wavelength of light microscope. So the resolving power of electron microscope is 100 times stronger than resolving power of the light microscope. 100 wavelength 100 times shorter, resolving power 100 times higher, stronger. That's how is it. 100 times 100 times shorter, wavelength 100 times shorter, resolving power 100 times stronger. Okay. So as I said, the smaller the wavelength, less diffraction, sharper image like this one lah. The shorter the wavelength, smaller angle theta. That means you will get you see less diffraction lah. Theta actually is the diffraction. Yeah, theta is actually the diffraction. Theta is actually the lesser the theta, lesser the theta, less diffraction. More the theta, more diffraction. Okay. So you can see a small wavelength, less diffraction, you turn up to become a very sharp image. This is the actual image, and this is the actual object. And the image you see also the same size. You also see the same size. Sharp image and no extra light. At the side here, no extra light, so sharper image. But this one, this is the actual, for the optical microscope is very long. So theta also very big. When theta big means more diffraction. More diffraction means the actual size is this big, but you have a lot of extra light at the side here. You see that? Because of long wavelength, a lot of diffract to the side. So you can see a lot of extra light. Here you can see a lot of extra blurry light. So the actual size is this one, but you see something this big. You see extra light. Maybe just now I did draw a image. Sharper image is something like this. Sharper image, you can see a sharp edge. Yeah, because no diffraction, less diffraction. But for the blur image, you see a lot of extra light because of more diffraction, extra light at the side. You see something like this, something like at the side here. So how do you know the actual size of this object? So what is the actual size of the object? Cannot see sharply, you can see blur image. This is optical microscope. Okay, electron microscope is so big. You see, it's so big. You see that scientist. This is the optical microscope is only this is the I think this is the optical microscope, this big, and this is the electron microscope, this big. And there are two types. There are transmission electron microscope. Another one is called the scanning microscopes. Transmission, that means the light pass through, the electron pass through the object. Scanning just scan the site. So transmission, you can get a 2D image, but scanning can get a 3D image for this. Okay, so again, less diffraction, smaller wavelength, less diffraction, more particle property. Because talking about diffraction actually is a wave property. Wave property, isn't it? When talking about diffraction actually is a wave property. Wave property. So electron microscope show less diffraction. Less diffraction means less wave property. That means less diffraction means what we can say is less wave property. When you say less wave property means it's more particle property. Electron behave more like particle. But if you say the optical microscope, it has more diffraction. More wave property. More wave property. Okay, so optical microscope, the light has more wave property because more diffraction, but electron microscope less diffraction because of small wavelength, less diffraction, less wave property. Now, and electron microscope can get a sharp image. This one blur image. When sharp image means you can see a higher resolution, you can see smaller the details. You can see if the resolving power is 100 times stronger, means you can see things 100 times smaller. Why we say about resolving power 100 times stronger? Resolving power 100 times stronger means it can see things 100 times smaller. Like bacteria, virus can be observed by electron microscope. Bacteria and virus cannot be seen by optical microscope. Cannot. Optical microscope can only see animal cell, plant cell. And I don't think the structure inside the cell also can be seen. Maybe it's a little bit the big nucleus, but you don't see the details. Yeah. So electron microscope can see because resolving power of electron is 100 times stronger. This resolving power means it can see things 100 times smaller. Okay. If the resolving power is 1,000 times stronger, then the detail you can see is 1,000 times smaller. You can see things 1,000 times smaller. That is what it means lah. Or I can say is, if the wavelength is all go back to the wavelength. If the wavelength is what I can say is, if the wavelength is 1,000 times shorter. Okay, now I want to just talk about this formula. Wavelength, resolving power versus wavelength and the details. Yeah. So if this is wavelength is 100 times, 1,000 times shorter, then the resolving power will be 1,000 times 1,000 times stronger. If you can increase the wavelength, if you can decrease the wavelength 1,000 times shorter, means you can get 1,000 times stronger resolving power. You can see things 1,000 times smaller. You can see details 1,000 times smaller. You can see things 1,000 times smaller. Okay. So how to change the wavelength? Manipulate the voltage by using high voltage. By using high voltage, you can get a very short, small wavelength. Okay. I think that's it for this comparison. I think it's very clear enough. Okay. Anything you don't understand, please leave a comment, and let's move on to the problem solving videos. Bye.